Welcome to my channel on chemistry lessons. This is an A-level chemistry video and it looks at isomerism in organic chemistry. So by the end of this video then, you are going to be able to recall and identify different types of isomerism. First up though, if you don't subscribe, please do. Your support is very much appreciated, and please take advantage of the likes and comments features and let me know what you think. So, isomerism then. There's actually two subgroups to isomerism. There's structural isomerism and stereoisomerism. And then there are other subgroups. So there's three types of structural: chain, position and functional group. And there are two types of stereoisomerism: geometric and optical. And what we're going to do is we're going to go through each one in turn. We're going to define them and then we're going to look at some examples. First off then, definition for an isomer. An isomer is compounds that have the same molecular formula, in other words, the same number and type of atoms. However, they are arranged differently, and that gives the molecules different properties. Let's move across to structural isomerism then. So structural isomerism means they have the same molecular formula but a different structural formula. Again, if you haven't seen previous video on structural formula, I suggest you do look at that. The three subgroups of structural formula then, we have chain isomerism. Now, chain isomerism is when the molecules only differ by their arrangement of the carbon atoms in the base chain. And the two main examples here would be straight chain and branched. So if I pick a molecule, if I go for C5H12, now you might assume that that's just pentane, and pentane would be one of the isomers. So we could have a 5-carbon straight chain. This would be a straight chain isomer, C5H12. And this would be a displayed formula that I'm drawing here. It is much quicker and easier to use skeletal, so I will do from now on. I'm going to use skeletal from now on. If you're not comfortable with skeletal, then we need to look at previous videos so that we are. So that's the skeletal of pentane, and that's the displayed for pentane. The other isomer, or a branched isomer, would be 2-methyl-butane. Or I could also have dimethyl-propane. So these would be known as chain isomers. A position isomer. This is when the molecule differs by the position of the functional group. So we won't have functional group isomers of alkanes, because alkanes is a very simple basic functional group where it's just carbons and hydrogens. We can though have position isomers of alkenes. For example, that's but1-ene. If I move that functional group to the middle, that's now but2-ene. So that's a that's a position isomer. I could also have a position isomer of a haloalkane. That's 2-bromobutane. Or I could have 1-bromobutane. They too would be classed as position isomers of bromobutane. Functional group isomerism then, we have the same molecular formula this time, but the functional group is different. And these are quite rare. And we're going to look at two examples as cyclic alkanes and alkenes, and aldehydes and ketones. First example then, a cyclic alkane. If I draw cyclohexane, that is in fact C6H12. Or if I draw hexene, They are both C6H12. However, the one on the left is classed as a cyclic alkane and has similar chemical properties to alkanes. The one on the right is an alkene and it has similar properties of alkenes. Less common then, and not necessarily covered too much in your BTEC spec, would be aldehydes and ketones. If I look at propan-al looks like this. Propan-one looks like this. So this is propan-al and propan-one. This is an aldehyde on the left and this is a ketone on the right. That's actually a different functional group. But as I've said, you don't cover those in much detail in this unit. It's mostly your alkanes and your alkenes that you need to be concerned with. So back to the beginning then. So we've covered the three types of structural isomer. We now need to look at the stereoisomerism. Definition for a stereoisomer: they have the same structural formula but different 3D arrangement in space. So notice how that's definitely a different definition to your structural isomer. Your structural isomer had different structural formula and same molecular formula. This time for a stereoisomer, they do have the same molecular formula, they do have the same structural formula, but it's a different arrangement in 3D space. Two types of stereoisomerism then. We've got geometric isomerism, sometimes called EZ, and this occurs in our alkenes due to the restricted rotation around a double bond. That means that double bond locks the groups in place and there's no free rotation. That bond can't rotate. Let's have a look at some examples then. So I'm going to draw my carbon-carbon double bond here. I'll draw a carbon-carbon double bond on the right. We've got a CH3 and I'm going to put a H, and then on this side I'll put a H, and again I'll put a CH3. So in order to have stereoisomerism, each carbon in the double bond must have two different groups on each carbon. So this has a CH3 and this is a H. These two groups are definitely different. And again, on the right hand side, we must have two different groups, which we do. We have CH3 and H. They are different groups. So what I can do is if I change the position of those groups, or just one of them, let me see, we've now got a different arrangement in space. So in this case, the CH3 groups are on opposite sides of the double bond, and on the left hand side, those CH3 groups on the same side. Now, I have done a video on or detailing the EZ isomerism. So again, I suggest you watch that first because this is just a real quick overview of geometric isomerism. I do go into detail and we do use the rules of assigning priority. So I do suggest you watch that video at some point and you'll see in detail how we identify and name those geometric isomers. Okay, the final type of stereoisomer is the optical isomers. And this is identified or defined as non-superimposable mirror images of each other. And they most commonly occur when a carbon atom has 4 different groups attached, and we call this a chiral carbon or an asymmetric carbon. So this type of isomerism is actually covered in second year specification, and you will find separate videos on that. However, just to give you an example, so it's a chiral carbon or a carbon with 4 different groups attached. So I'm going to just pick a carbon with a Cl, a CH3, an OH, and a H. So that's got 4 different groups attached. So to show you how we can draw these isomers, I need to draw them 3D. So I'm just going to draw the tetrahedral shape, and I'm just assigning these groups randomly. I've got 4 different groups, and I've drawn this as a tetrahedral. Now what I'm going to do is draw the reflection of that tetrahedron, or that tetrahedral shape, being careful to make sure that it does actually match the mirror image. And I've now drawn the two optical isomers of that molecule, mirror images. And as I've said, that's covered in more detail further in the spec, and you will find it in my second year content. So there's your big overview on isomerism. And as I said during the video, I do strongly advise that you watch the video on geometric EZ and you make sure you know that one in a lot more detail. And the optical isomerism will follow on in second year as well. Hopefully you found that video useful then, and thanks for watching.